I wanted to give a status report on some of the work that we've been doing on developing new linear solvers and preconditioners for higher order finite elements, and doing the GPU acceleration, getting this to run really fast on GPU. And this is work that I did together with a lot of people on the MFEM team, in particular, Tanyo and John Camier. And so before I talk about the higher order solvers, I wanted to motivate a little bit the use of higher order finite elements. In MFEM in general, we support arbitrary order finite elements, and there's a big focus on supporting higher order methods. And this is for a number of reasons. Higher order finite elements promise higher accuracy per degree of freedom. This can be seen both in the asymptotic error estimates, but also on real world problems, solving challenging physics, turbulence, and so on. We have good empirical evidence that you get better, more predictive results using higher order methods, better symmetry preservation. You can handle problems with singularities, doing things like HP adaptivity. So there's a lot of benefits. And another important benefit is, we're entering the era of GPU-based exascale supercomputers, and these higher order methods are really a lot better suited for these types of architectures than low order methods are. And we're going to see a lot of evidence of that in this talk. And that being said, there are some aspects of higher order finite elements that still remain challenging. In MFEM, with our partial assembly and GPU support, we've really optimized, there's been a lot of hard work by people on the team to really optimize the evaluation of the operator, computing its action. That can be done super fast. But solving linear systems with these operators, inverting the matrix, is still expensive. The matrix is extremely ill-conditioned. It's expensive to assemble. Storing the matrix has a very high memory cost. And so ideally, what we would like is to construct linear solvers that converge quickly, don't require too many iterations, have low memory requirements, are applicable to different types of physics that are not specific to only one type of finite element space or just one physical problem. And since this is MFEM workshop, on the MFEM and software side, ideally, we'd like these solvers to run on the GPU from start to finish and be easily accessible and easy to use in MFEM. If you have an MFEM-based code, it should be pretty easy to plug these guys into your existing code. So these are our goals, and I'll describe some of the work that we did to try and address them. Before I start describing the solvers, I wanted to motivate the use of matrix-free methods. So one of the big challenges with higher solvers is you have to go matrix-free, and this can be seen pretty easily just by looking at some scaling arguments with the polynomial degree. So here P is the polynomial degree, and D is the spatial dimension. So the number of degrees of freedom scales like P to the D. So in 3D, this is just P cubed. And for matrix-based methods, as soon as you assemble the matrix, you get within each element an all-to-all coupling. So you have P to the 2D non-zeros. In 3D, this is P to the 6. So that's where the high memory cost comes from. And it's even worse when you look at the number of operations required to assemble these matrices. In the best cases, P to the 7, but oftentimes in a lot of practical situations, it's going to be P to the 9 operations to assemble this matrix. So this is prohibitive. Before you even start hitting the higher values of P, even for moderate polynomial degree, this is prohibitively expensive. On the other hand, matrix-free methods have optimal memory usage. It's O of 1 memory per degree of freedom. And the operator evaluation is P to the 4, so it's not optimal in that sense, but it's linear operations per degree of freedom, and it can be optimized really well. It can go really fast. So matrix-free methods really get around this bottleneck of working with the matrix representation. The issue is it's difficult to construct preconditioners if you don't have access to the matrix entries. You can't take something off the shelf like AMG and just hand it a matrix if you don't have one available. And there are a number of approaches that can be used to get around this limitation. For instance, you could do P multigrid. But in this talk, I wanted to focus on low order refined preconditioning. This is an idea that's been around since it was introduced in 1980 and has kind of a history of development since then. And the idea is really simple and elegant. You start with a higher operator defined on a coarse mesh. And the matrix here, this is kind of a cartoon of the sparsity pattern of this matrix. It's going to have these big dense blocks that correspond to the elements. And so we don't want to form this matrix AP. We don't want to form it and store it explicitly. It's too expensive. So what you can do is you can take this coarse higher mesh and you can subdivide it into smaller elements, but these elements are lowest order elements. And then you can assemble the matrix on this refined mesh, this low order refined mesh. And you get a matrix that has a sparsity pattern that looks like AH. So it has the same dimensions as AP, but the number of non-zeros per row here is constant, independent of the polynomial degree. So this is, and again, this is a matrix that comes from a low order discretization. So we can take an off-the-shelf solver for low order finite elements and construct it using AH and apply it to our original problem AP using the matrix-free action. Certainly, that's something that you can do. It makes sense to do. The question is whether it's a good thing to do, whether you'll get a good preconditioner. And the answer to that is actually yes. So there's this theorem from Canuto and Quartaroni that say if AP and AH are H1 discretizations of, say, a Poisson problem, you can also have a mass matrix. So these are higher order and lower order refined diffusion problems. Then AH is spectrally equivalent to AP, and the constants of equivalence are independent of H and P. So you'll get kind of uniformly good, if you do this procedure of constructing a good preconditioner for this low order sparse guy, you'll get uniformly good convergence independent of the problem size and the polynomial degree if you apply it to AP. So this theorem holds for discretizations in H1. And together with Clark Dorman and Sanyo, we extended this to the full de Rham complex. So this was, if we want this technique to be applicable to different kinds of physics, we're going to want to be able to solve, for instance, definite Maxwell problems or grad diff problems. And so you can do this approach also on these problems if you use something called the interpolation histopolation basis, which is a kind of special but also very natural basis for these vector finite elements. So this lets us handle, different kinds of physics using the finite element de Rham complex. And so these are just simple 2D model problems, but it's showing the kind of convergence you can expect iterations on the y-axis, polynomial degree on the x-axis. At p equals 1, it's always going to be one iteration. You'll get some pre-asymptotic increase, but then it's going to level out and get a p-independent convergence. This is for Poisson, this is for Maxwell, and this is for grad diff with Nedelec and Ravi-Artema elements. So in general, the algorithm looks as follows. We have a setup phase where we do our higher order operator setup, like in partial assembly. And now we have an extra step of assembling a low order refined matrix. And then we send that, for instance, to AMG or whatever solver we might be using. That's our setup. And then we move on to solve, which is a CG iteration. Every iteration, we have our higher order operator evaluation using partial assembly, and then the preconditioner application or the AMG V cycle. So what we're going to do here is just delegate everything having to do with AMG to Hyper. The Hyper team has done a lot of really great work getting their AMG to work fast on GPUs. And this kind of illustrates a nice property of this low order refined preconditioner. You can use any matrix-based preconditioner and just apply it to the low order refined system. So if there's a new architecture or a new solver library comes out, you can just plug it in. You don't need to, it's non-intrusive. You don't need to change anything having to do with the discretization. For the higher order operator setup in assembly, we use partial assembly. This has been a huge effort in the MFEM project and in the SEED project in the ECP. Representing the operator not as a matrix, but as this kind of nested product of these terms that are applied for the most part matrix-free and using some factorization and really optimizing this all the way. So that's the approach that we use for the higher order operator. And I mentioned at the beginning that higher refined elements are better suited for these GPU-based architectures. This is an illustration of that. So I'm going to be showing a lot of these throughput plots. So I'll take a moment to explain how to read them. This is on the y-axis throughput, degrees of freedom, millions of degrees of freedom per second. So higher is faster. This is a measure of how big the problems are that we can process in our kernels per second. And on the x-axis, it's degrees of freedom. So this is problem size, basically H refinement, and the different curves are different polynomial degrees. So here what we see is that the curves are kind of separating as you go higher in polynomial degrees. You get higher performance as you go, you get better performance, actually runs faster as you go higher in polynomial degree. The peak here reaching about 700 million degrees of freedom per second. So this is pretty fast. This is on one V100 GPU. This is for the setup that you just do kind of once at the beginning of the problem. Then every stage iteration, you have the higher operator evaluation. This is computing the action of the operator. And here, the peak here is about 1.6 billion degrees of freedom. This is using MFEM's native backend. But if we connect with libseed and use the CUDA-gen code generation and kernel fusion, then we can get up to this 3.2 billion degrees of freedom per second being processed in these operator evaluation kernels. And we see the typical behavior for higher methods on GPU. Higher order actually gives you, independent of the better accuracy and more predictive, it just runs faster on the GPU. So that's exactly what we're seeing here. Now, once we have the higher order operator set up, we need to do this additional step of assembling the low order refined matrix. That's kind of the additional work we need to do for these preconditioners. And until now, this was a major bottleneck. This was taking the majority of the time to the solution. We had to take our coarse mesh, form a refined mesh, do all the bookkeeping associated with the mesh topology, and then do the matrix assembly on this refined mesh. For a while, we were doing that on host. More recently, we started doing it on device. So at least we got GPU acceleration there. But it's kind of generic matrix assembly code that doesn't take into account the structure that you can kind of see is inherent in these low order refined meshes. So we developed a new strategy, a macro element strategy, which is basically that you perform all of the work at the level of macro elements. So here it's showing this is kind of the coarse mesh, and then this is one macro element with the refinements here. So we don't generate the low order refined mesh. We work only with the data structures of the high order coarse mesh. We reuse everything from the high order operator setup. And then we make use of the fact that we know that locally within a macro element, we have a Cartesian structure. And so this really saves a lot of work in pre-processing and bookkeeping. And it also leads to a natural threading strategy that we can use one block of threads per macro element and then thread over each of these sub-elements. So we do that and we assemble the local matrix like it's typical in finite element assembly. You assemble the local matrix, but the difference is in contrast to typical finite element assembly, the local matrix isn't dense, it's sparse. So you get a sparse local matrix, and then these are placed into a global parallel sparse CSR matrix that can be sent to AMG. So here's the performance gains that we got by doing the strategy. These plots, so left is the previous strategy, right is the new one, and these are not including any of the pre-processing associated with the mesh. I'll show that later. This is just the matrix assembly. So we go from a peak of about 10 million degrees of freedom per second to up to more than 20 million degrees of freedom. So it's more than 2x performance increase, and also for these larger problems, you get better sustained performance. And if you compare with the pre-processing steps with all the bookkeeping that I mentioned, that was what was really killing our performance. So here, this is almost a 100x speed up. We did, so you might notice that this p equals 1 is a little bit low here with the new method, and we did some work on optimizing it. This is stuff, work that John did. And so these are the final results that we get. The peak performance for assembling the matrix is about 21 million degrees of freedom per second on a single GPU. And we're recovering the standard behavior for higher defined elements that we get faster performance as the order of the method increases. This is a breakdown of the relative times spent in the different algorithmic components on the CPU and GPU. So this is interesting if you just compare the CPU and GPU really are different beasts and they behave differently. They're different bottlenecks. But for our purposes, what I wanted to emphasize is that this little red slice here and here on the GPU, this is assembling the low order refined matrix, which used to be our bottleneck. Now it's really insignificant. It's about 10% of the total runtime. So these optimizations allowed us to basically greatly reduce the significance of this low order refined assembly step. I mentioned that these methods work for problems in HCurl and HDiv with Nedelec and Ravier-Thomas elements, and we get good performance there. So the same strategy for assembling the matrices applies in those cases, and we get good performance here, 25 million degrees of freedom per second, and for Ravier-Thomas, 15 million degrees of freedom per second. 150 million degrees of freedom per second. Excuse me, I read it wrong. So we get the reason that there's a difference between Nedelec and Ravier-Thomas has to do with the connectivity structure between the different finite elements, how they're glued together. So for problems in these vector finite element spaces, you can't apply vanilla AMG to the matrix and expect to get good performance. You need to use specialized solvers. So we're using Hyper's auxiliary space preconditioners, AMS and ADS, to solve these problems. Those require, it's close to black box, but they do require some additional inputs beyond just the matrix. So they might require a discrete differential operator in the form of another matrix and also mesh vertex coordinates. So we need to do a little bit of extra work preparing these extra inputs to send to Hyper to construct the preconditioner. And that's also implemented, and these are really fast, using properties of this interpolationist opulation basis, the special basis that I mentioned earlier. These discrete matrices are incredibly sparse. The sparsity doesn't increase. You don't get increased number of non-zeros with increased polynomial degree, and you can form the matrices really quickly. So discrete gradient can be formed in the performance we're getting. The throughput in these kernels is 12 billion degrees of freedom per second. And for instance, preparing the vertex coordinates of the lower order refined mesh in the format that Hyper needs is around 22 or 23 billion degrees of freedom per second. So these don't even show up in the profiler when you look at the performance. All of the numbers up until now were on one GPU. These were on one V100. Of course, we're not interested only in one GPU. I mentioned at the beginning, GPU-powered exascale supercomputers. So we are interested also in scaling to many GPUs. Here are some scaling results. This is strong and weak scaling on one plot. So the solid lines are strong scaling, and the dashed lines that connect them are weak scaling. So this dashed line at the end is the ideal strong scaling, and horizontal is ideal weak scaling. And we see that for the different components, assembling the lower order refined matrix and the sparse matrix preparation and so on, assembling the higher order operator, we get really good strong and weak scaling up to 1024 GPUs on problems up to, for these tests, up to 1.1 billion degrees of freedom. So in the little time that I have left, I wanted to present some results. So I didn't discuss the methods, and I don't have time to, but you can also apply this to non-conforming meshes with adaptive mesh refinement. If you think about how to set up the lower order refined problem, it kind of makes your head hurt when you have non-conforming meshes, but we have an algebraic way of doing it, and it works really well. You get a constant number of iterations with respect to polynomial degree. You can solve big problems on non-conforming meshes in a couple of seconds on the GPU. And I wanted to show an electromagnetics problem. This is solving for the magnetic field induced by a current running through this copper coil in air. So this is a problem with 290 million Nedelec degrees of freedom, p equals 4. We use AMS to solve the H curl problem, and it converges in 22 iterations. You have to do Poisson solve in H1 that requires 45 iterations. The total time to solution, everything included for this problem, is 26 seconds running on 320 GPUs. So this is a slightly different coil. It's just a cool visualization. This has more loops, but this is the problem setup that I was describing earlier, just tracing out the magnetic streamlines. I apologize that I'm running a minute or two late, so I'll wrap up really quickly. This is just a code snippet of what it looks like to add this to your code. In most cases, it's going to be one line of code, and this will get you AMG or AMS or ADS, or you can just bring in your own solver. It could be a parallel direct solver. So with that, I'll just leave my conclusions up, and I'd be happy to take any questions. Thank you.
Thank you, Will. So if we have a PDE where take for example a diffusion equation where the coefficient depends on space, when you do the low order refined mesh, do you the operator discretized on the refined mesh, does it take the same values that has on the coarse mesh for the coefficient, or does it interpolate it?
So the lower order refined, the vertices of the lower order refined mesh are at the Gauss-Lobato points in the coarse mesh, and the way that this works is that the values of the coefficients will be evaluated exactly at those Gauss-Lobato points. So it basically takes the Gauss-Lobato integration rule on the coarse mesh, evaluates the coefficients there, and then uses those in the assembly routines, interpreting those nodes, those nodal points, as the vertices of the lower refined mesh.
But that will lead to a non-conforming values of the coefficients. So do you see what I mean?
What do you mean by non-conforming values?
Like if you the function, the viscosity in your defined on the coarse mesh will not match the one on the refined mesh.
Right.
That may lead to the preconditioner will not be efficient.
So it will depend on the integration rule that you use for your higher order system. So if you do something like SEM, spectral element method, then the integration points that you use for the higher order system are exactly the same points, and then the coefficient values will be exactly the same. If you do a more traditional finite element method where you use maybe some higher precision Gauss-Legendre rule, then yes, you're evaluating the coefficients at slightly different points. If your coefficient is well resolved and you have enough smoothness, the error should be small. In general, it's a preconditioner, and you're going to get some errors like that basically appearing in your spectral bounds. But it should not be. We've done a lot of tests with variable coefficients, piecewise constant coefficients, coefficients with steep gradients, and in general, these solvers work well. There is some dependence on the coefficient contrast, but it can handle non-trivial coefficients.
So just
thanks, Will. So I think we're gonna have to move on to the next talk, but why don't you guys take this on to Slack? It sounds like a good discussion.